VVT activities during use, maintenance, and disposal. Focus on a bridge inspection drone presented by Flor Manzanares, Juan Yepes, Cesar Venegas, and Sergio Flores. We will cover the main VVT activities during maintenance and disposal, including development of VVT plan for system maintenance, verification of integrated logistics support plan, perform ongoing system maintenance testing, conduct engineering peer review on system maintenance process, develop plan for system disposal, assess the system disposal plan, assess system disposal strategies by means of simulation, assess ongoing system disposal process, and conduct engineering peer review to assess system disposal process. The purpose of the system use and maintenance phase is to operate the system in its actual anticipated user environment to fulfill its intended functions. During this phase, the system requires a variety of VVT activities as routine operations performed by either the system or manually by the operators. Corrective maintenance is the identification and removal of non-critical system defects. Emergency maintenance is the unscheduled corrective maintenance, for example, unexpected failure on drone, broken part on collision, propeller damage. Perfective maintenance is upgrading the system functionality and performance in a rather limited fashion. This is improvement on system software, stability of software. Adaptive maintenance is modifying the system to keep it up to date with its environment. For example, the addition of new motors or a new camera. Preventive maintenance is the identification of activities performed in advance of an immediate need for system repair or in advance of accumulated deterioration, cleaning the propellers, or providing maintenance to the motors. We created a list of activities that need to be performed to the system after a certain level of operation. Here we have the activities before and after every flight, after 50 hours of flight, and after 200 hours of flight. It is important to notice that a strategy of frequent maintenance efforts is more effective than infrequent major maintenance. Not performing the required maintenance will cause an accident or loss of equipment. There are many obstacles related to maintenance. Planning maintenance process. All maintenance activities are carefully planned in advance. Maintenance and operational conflict. The VVT team should plan perfective, adaptive, preventive maintenance in a flexible enough manner to accommodate unforeseen schedule changes. Legacy systems. The VVT team should review maintenance plans of such legacy systems very early on to identify potential legacy problems. The integrated logistics support plan consists of 11 steps, but we will only focus to cover those steps that apply to our bridge inspection drone system. Step 1. Verify integrated logistics support management. Our methodology to evaluate support processes: discover, remediate, manage, and evaluate. Step 2. Verify maintenance. Verify that the maintenance plan provides a description of how, when, and by whom the maintenance will be performed. In our case, this will be performed by certified technicians. For maintenance, test, and support equipment, we will verify that the requirements for testing equipment, maintenance, and calibration are met. Our project will outsource these activities to calibration maintenance services that comply with industry standards. Step 3. Perform test and evaluation. Test program will verify that the plan identifies applicable regulations, directives, and other documents. We'll develop a test and evaluation plan, an operational test and evaluation, and we will test support for completion of the DT&E and of the OT&E. Step 4. Verify supply support and provisioning. This includes verification activities for initial installation, repair parts on site and off-site, and procedures for inventory utilization. This is a simple explanation of how spare management will be prioritized. If there is no explanation for the use of the spares, then we will minimize their use. If it is common sense based on the input of the technicians, then we will consider a moderate use of the spares. And if by the use of the quantitative methods and based on forecasting, it is reasonable to supply more spare parts, then they will be supplied. For the disposition of non-serviceable, obsolete, salvage, or excess equipment, cannibalization plays an important role for our system as we will need to remove parts from the drone for replace, repair, and/or maintenance. We have put a process in place to document and keep track of cannibalization and removal of equipment from inventory. This is a sample of the template that will be used to document the removal of parts from the drone or removal of equipment from inventory. The person responsible for filling it out will need to include information such as equipment or part tag number, description, person requesting the removal, person who authorized it, and the process of the disposition of this equipment or material. Step 6. Verify technical data and data management. Management techniques to ensure the data are properly specified and provided, which includes data management and data deliverables. This is an example of how we will manage data collected. We will provide a definition of what we consider each data quality dimension means. We will provide the measure, scope, and types of measure in order to manage the data. Step 7. Verify configuration management. This includes organization responsible of configuration management, either hardware or software, configuration items, configuration identification, and on-site configuration audit. Once the initial configuration for the bridge inspection drone has been verified, approved changes to the configuration must also be verified. Step 9. Verify personnel and training. Operation and maintenance training of the system equipment, including personnel, training requirements, training equipment, training tests, and evaluation. Step 11. Verify computer resource support. One of the main subsystems of our bridge inspection drone system is the software. The software will store, categorize, and report the data that was captured. However, there will be changes to the software to either enhance it or to fix a bug. So in order to ensure that the software will keep functioning as expected, all changes requests need to be approved and documented. Therefore, a well-defined change policy document must be implemented. Our change management policy will ensure that software changes are minimally disruptive to services, that changes are coordinated and logged so conflicts or duplications of efforts does not occur, ensure that the changes are tracked, change requests must be communicated to all parties affected, all changes must include an impact assessment, and that the software must be tested in a separate yet similar environment to production. Perform ongoing system maintenance testing seeking to optimize system availability and maintain this availability within technical, performance, legal, commercial, and environmental parameters. Maintenance will focus on testing the target system, repair failed components, or replacing them when the cost of repairs exceeds replacement cost, requires a planning and managing of the process in an optimal manner. Maintenance implementation will minimize the overall system cost by means of preventive maintenance, repairing everything as quickly and cheaply as possible, and will optimize the repair-replace strategy to save time and money. Maintenance encompasses the set of activities that aim to sustain a system, a condition deemed necessary for it to properly fulfill its functions. On Figure 3.4, cost of maintenance versus level of preventive maintenance. Here, the failure cost decreases exponentially with the amount of preventive maintenance, whereas the cost of preventive maintenance is drawn as an increased linear function. Therefore, the total cost of maintenance is the sum of these two components. We actually want to be in the sweet spot between failure cost and preventive cost in the optimal maintenance strategy, right here. During peer review, we were asked, check conditions of propellers, but how will this be done? Basically, we will remove the bug remains from the propeller and clean it with a damp towel. We'll inspect the propellers for hairline cracks in the body, edges, and near the hub. We will apply flexing pressure to the propeller to confirm its mechanical integrity. It is important to notice that the steps for each of these activities is not specified on this table, just a basic description of the task. The specific instructions will be provided in a separate and independent document. On the VVT activities during disposal, the purpose is to properly dispose of system and its element upon completion of its useful life. The life cycle of our drone is about 2.5 years. Our basic plan for disposal consists of 4 steps. First, we will identify the major components of the system. We'll break down the drone into components. We will identify whether the components will be recycled, upgraded, or disposed. And finally, we will ensure that the proper disposal is met. We will identify the major components of the system. The major components of our bridge inspection drone system are drone frame, propellers, motor, battery, camera, and CPU. For the breakdown drone into components, here we have the propellers, motor, frame, CPU, battery, and camera. We identified that the battery and motors will be recycled, the CPU and the camera can be upgraded, and that the frame and the propellers will be disposed. We identified an appropriate disposal strategy and plan, making sure that we comply with safety and environmental regulations and that we provide a maximum economic benefit. The VVT team should also verify that no further practical use for the system is there, and that the system and use scenarios comprise economic value, which can be either by redeploying the system for a different purpose, reclamation of the system, or recycling usable portions and reselling the system to other users. In many cases, disposal strategies are ignored. Most systems have few or no requirements associated with disposal. Some systems have materials that have disposal requirements due to hazard and safety considerations. Disposal phase is considered as the final phase, addressed and verified during the system definition and design phases, and assessed by the VVT team. It is important that sensitive or confidential data stored within the electronic equipment must be permanently erased or destroyed before transferring the system for reuse or disposal. The bridge inspection drone system does not store confidential information, yet it must dispose irrelevant electronic data and electronic media. Electronic media used by the bridge inspection drone is solid-state drives, which include USB storage devices and camera cards. Destruction methods are physical, either by melt or pulverization. We will assess the environmental impact and level of recyclability. An advantage of this approach is that it provides realistic results in estimating the amount of salvage material to be recycled, either by disassembly and recycling activities. We will verify that the ongoing system disposal process is performed according to the applicable environmental and health regulations and policies, verifying that the remains of the system contain no harmful substances to the environment, that the disposal process does not constitute any health risk, and that the economic maximization of the residual value of the obsolete systems is met. Once again, it's important to conduct an engineering peer review. The objective of this activity is to utilize engineering peer review in order to assess whether the ongoing system disposal process is performed in accordance with the system's disposal process plan and according to the applicable environmental and health regulation and policies. Questions? Thank you.